Hello everyone and welcome to the Backbenchers Academy by Rohit Verma, and here we present our second video based on optics part B, that is the refraction of light through a prism. So we are going to study today what a prism is and how a prism is used for the refraction of light, which is how bending of light takes place through a prism when it changes its medium. So without any delay, let's proceed on to our very first topic. So what is a prism? Let's see. A prism is a transparent medium bounded by five plane surfaces with a triangular cross section, as we can see. So if we see over here onto the right side of this particular sheet, the slide, that is this particular shape. So as we see, this shape resembles the triangular cross section area that is highlighted with the yellow right now. This is the cross section area, which is triangular, and it's a three-dimensional object with five plane surfaces, three on sides, one on the front, one at the back. So this is what exactly a prism is defined as. Then further on, let's move into detail how it is used for the refraction of light through a triangular prism. As we see here in this diagram, we have the triangular cross section of a prism which is labeled with A, B and C, wherein an incident ray is coming, which is named as OP. This being the incident ray, which is traveling inclinedly towards the surface AB of this prism ABC, wherein it creates the angle I1 with respect to the surface of AB, and which we found with the reference of the normal n. Now since we are moving from air, like this is air outside, we are moving in from air into glass, since a prism is actually made up of glass. So we are moving from air to the glass. What exactly happens is refraction of light happens since the mediums are changing. Moreover, the angle of incidence is over here, which is this one, is not really 90 or 0. Sorry, not really 90, it's not really 0, since it is not coming perpendicularly on the surface. So we've satisfied both the conditions of refraction of light, and hence the light will bend. Now earlier the light was supposed to go straight this way. This was the actual path which the light was supposed to go onto. But at the same time, since we have changed the medium and moreover, the bending will happen. So moving from the rarer to the denser medium, we are moving towards the normal. So this is how we've moved. This green particular arrow shows how we have moved. The yellow line over here, the yellow arrow is showing how we should have moved earlier if there was no deviation. But here we have a deviation, and how much deviation we had? We had deviated by an angle of delta 1. This is the first angle of deviation inside, wherein R1 stands for the first angle of refraction. Now the light travels straight away, which is the line PQ. It travels straight away, and at point Q, it further changes on the medium again from glass to air. Now outside is again air. So we are changing the medium once again. That means again refraction will take place, and this time we're going to bend off away from the normal. So this line would have gone straight away to the this particular direction. It should have gone in a direction where there would, if there would have been no deviation, the ray should have gone this way somewhere. But since we have here a phenomena of the bending of light, therefore it bends away from the normal, and this is where we actually bend off. And this is our angle of emergence. This is the angle through which we emerge. Now, if we see how the light has come out, that is this, the blue arrow, this way, this one, this is the emergent ray, and how the light was coming initially without any deviation or without any bending, which was this. If we compare these two directions, then there is an angle of the total deviation which takes place here. That is called del, or the actual angle of deviation. So what is angle of deviation? If we see here, it is the total angle by which an incident ray has deviated or shifted with respect to its earlier position, which initially it was on. So let's understand a little bit more about angle of deviation onto our next slide. I hope you understood this process. Deviation can be defined as the angle between uh, our direction of the incident ray and the direction of the emergent ray. So if we compare the incident ray and the emergent ray, then the angle that we have created between those two, which was like earlier it was supposed to go this way, but later on it deviated up this way. So this is the angle we are talking about. This is called angle of deviation in this concern. And moreover, so this is what we call as angle of deviation, and it has a special symbol called delta. Delta is the representation symbol. Moreover, the important formula associated with the angle of deviation are: first one, del equals I1 plus I2 in one bracket, which is added together, minus R1 plus R2 in a separate bracket. So it means the difference between the sum of the angle of incidence and the angle of emergence, which is I1 and I2 respectively, and the sum of angle of refraction 1 and refraction 2, which is R1 and R2 separately. So second formula which we need to know is A plus del equals I1 plus I2, where A means angle of prism, del is the angle of deviation, I1 and I2 are the angle of incidence and angle of emergence respectively. But these two formulas are primarily important with respect to the numerical perspectives, and there are often some numericals based on these two formulas, so we must know this. Moreover, now let's further proceed on to our next. What angle of deviation depends upon. So if we observe here, there are four things on which angle of deviation depends on. Number one is angle of incidence, and the variation dependency will be discussed in the next slide, because actually angle of deviation depends very uniquely or very specially with the angle of incidence. Second thing is the material of the prism or the refractive index of the prism, where it is directly proportional, which means more will be the refractive index of the prism, greater will be its angle of deviation, which means the more denser the prism will be, the more will be the bending caused due to it. Third thing is angle of prism, which is the topmost angle. So if we see, if this is the prism, if you observe here, this being the base B, let's suppose, then the angle on this topmost part, this angle right on top, is A, that is angle of prism over here. So if this angle of prism is more, then more will be the bending. So it's directly proportional, which means that higher will be the value of the angle of prism, more will be the deviation produced, which is angle of deviation will be high. Then the fourth thing is the color or the wavelength of light, which is inversely proportional. This is important. See, the other two were directly proportional. This is unique. The first one, angle of incidence, is unique, whereas the last one, that is color or wavelength of light, is inversely proportional, being a very different dependency with respect to the other three. Because if you observe here, it means more the wavelength of light, less will be its deviation, which is pretty obviously understood. Because if you see all the danger signals that we see around us, maybe when you stop a car, you see that the signal at the back of this car light turns to be red, because red has the maximum wavelength, so it is least deviated. That is the reason why even when you use a car and you apply brakes, then the brakes are pretty clearly visible during rain, foggy season, or any other particular such circumstances if are there. So that is the reason why they are least deviated. That means more will be the wavelength, which is maximum for red, lesser will be its deviation, which means red color in WebGyor is the least deviated, whereas violet, being the least one in terms of wavelength, is maximum deviated. So this was about the dependency of the angle of deviation on various factors. Let's understand about this factor further once again, which is angle of incidence, that how is it unique, into the next. So here everyone, so let's see how is the angle of deviation depending over angle of incidence. So if we see here, there's a graph that shows angle of deviation being on the y-axis and the angle of incidence shown over the x-axis. And if we observe this curve, there's a curve which is represented here in this manner, which decreases first. That means that angle of deviation first is decreasing when the angle of incidence is increasing, which shows that initially there is an inversely proportional relation. I means inversely. Then it reaches to its minimum or least position, which is this. That is the minimum position, least position. If you observe into the graph, then this is the minimum value which it can attain. And then further after this, it starts increasing, which means that when we, after this particular line, when after this line, when we are increasing the angle of incidence, even the angle of deviation is also increasing, which means it is directly proportional. So in this curve, D means directly proportional, I means inversely proportional. So angle of deviation was first inversely proportional to angle of incidence, then it received or got or attained its minimum value, which is called del minimum, that is the minimum angle of deviation. And later on, it became directly proportional, so it increased when the angle of incidence increased. So this is a very unique and a different kind of a relation which is established between the angle of deviation and the angle of incidence. Let's move further on to our next minimum angle of deviation. Let's see when is it possible to create a least angle of deviation for any light. Now, first of all, for any light, may it be a monochromatic light or a white light. So how can we create a minimum deviation? So angle of deviation can become minimum if, first thing, I1 becomes equal to I2, which means when angle of incidence becomes equals to angle of emergence. Number two, R1 should become equal to R2, which means that the angle of refraction should be equal to the second angle of refraction. The first one should be equal to second one. R1 equals R2 and I1 equals I2. So if we apply these two things together, both should be applied. This condition also should be correct and this also should be correct, not just either of them, both of them. So when both are correct, then we associate it with one formula which we've studied initially, previously, which is del plus A. We just saw one formula earlier, which was del plus A, which was coming up equal to the I1 plus I2. So we just observed this formula in like a few seconds back on one of the previous slides. And this was one formula which I told you is pretty important, as there can be questions framed on this. So if in this formula, if we see that I1 and I2 are equal, let's say they're equal to I. So this becomes del plus A is equal to 2I. And this del is a special del, which is del minimum. This is right here, del minimum, which is equal to 2I and minus A, because when we shift this A to the other side, it becomes negative. So this is what we get. Now where I is the angle of incidence over here or emergence, because both are equal. A is the angle of prism and del minimum is the minimum angle of deviation. So this is a special condition wherein the amount of deviation happening is least. Let's proceed forward to our next topic, everyone. Up to our next topic, which is real and apparent depth. As the name says, it's pretty easy. Real depth means the actual depth of a particular object or a certain particular thing or a substance from its point of assumption or appearance or observation. So it's actually the actual distance of an object. This underlined thing is nothing but the key point. This is the key point. This is important. It's the actual distance of an object beneath or under a surface as would be measured by submerging a perfect ruler along with it. And apparent depth, on other terms, in a medium is the depth of the object in a denser medium as seen from a rarer medium. So its value is always lesser or smaller than the real depth. So if you say practically, let's say if you're standing outside a pool, swimming pool filled with water, and you drop a coin inside the pool and you're observing the coin from outside, the depth which you will be able to observe will be actually comparatively less than the real depth. So what we are able to see is a virtual depth. That's what we call as apparent depth. Apparent, something that is appearing, something that is actually looking like it's true, but it's not really true. So it is just our assumption. It's just a hypothetical phenomena. So this is just, you can say, like a virtual reality thing. And when we connect these two particular terms, we get a formula. This formula is pretty important, which is apparent depth is equal to real depth upon mu. This mu is nothing but refractive index, which we've studied previously in one of the previous videos, the first video which we've done. And the refractive index obviously depends on the density of this medium. So let's say if we talk about water and air, the mu will be suppose given to you, real depth suppose is given to you, apparent depth we have to find. That means out of three parameters, we've been given any two, and the third one we have to find. So we can apply this formula. Now with the help of a diagram as well. As we see here, there is a boat, like a jet boat, and it has the actual depth. Now this thing is the actual depth of this particular boat, and there's a chest. If you see out here, this is the chest, like, or the chest you can say, or like a box sort of thing. So this boxing is being observed from a person standing on top. Now see, if you see, here is the person, and when he observes, he is not able to actually see the chest here at its actual position. He's able to see it here at its apparent position, and this is what practically happens to us. So the same thing we can understand, like when we look at our legs while standing in a pool filled with water, then our lower body appears to be shorter. That same thing happens because of refraction of light. Now let's phenomena happening when we see a bending stick in water. This we've discussed earlier as well, and in one of my previous videos you can see that initially we discussed that we have a spoon which is put inside a particular glass, transparent glass filled with water. Then the lower portion of this spoon, which is inside, seems to be bent because of refraction of light. Let's study some applications and consequences of the refraction of light, starting with these four particular consequences being the most common ones. First one is twinkling of light, as we can see here. The second one mentioned is that the sun rises a few minutes earlier and sets few minutes late from the horizon. The third one is water tank appears shallow, then its real depth. And the fourth one is a person's legs appear short while standing in a pool of water. Now the fourth one, if you see here, is something which we've already discussed, that we stand when we stand in a pool filled with water, and we are like half inside water. So when we look at our lower body, our legs appears to be shorter. So first let's discuss it in the sequence with starting from the very first one. Talking about twinkling of stars. So if you talk about twinkling of stars, if you see here, assuming, let's say this is the Earth, and I'm denoting it with E. So this is the Earth, and we have five layers of atmosphere surrounding it, like this. Let's suppose these are basically the five different layers which we have inside, starting from the bottommost to the topmost one, where after that it moves on to, so we've got one over here. This is one, two, three, four, and let's create another layer up here. So these are five layers. Outermost one is space. So this is S denotes space, E denotes Earth. We've got a star here, let's assume, and a star is extremely far off from us. So when the ray of light coming from the star approaches towards the Earth, it travels from five different layers, five, and all these layers have different densities. So that is the reason why there is refraction of light which takes place five times, five different times, starting from the point when it enters into the Earth's surface from the vacuum on to the sequence when it enters from one layer to the other layer. So when someone is here on Earth, let's suppose, and is trying to see the star in the night sky, so at a certain point of time wherein the light coming from the star is able to approach to our eyes and is able to we are able to receive it, so then the star appears to be bright. But at a moment, because of bending happening five times up here, so at a certain point of time, if the light is unable to reach to our eyes, it will obviously scatter away, or it will diverge from its place, you can say from its ideal path. It will basically be moving on to some other place, or it will lose its path, the ideal path which it should follow. And that is the reason why the star appears to be dull. So when we are able to receive the light, it's bright. When we're not able to receive the light because of refraction of light, it's dull. So this phenomena keeps happening because it's not a continuous flow of light coming up, and that is exactly the reason why this happens, that stars appears to be twinkling. They're not really twinkling, they appear to be twinkling. So sun is the biggest star. Why doesn't it twinkle? Because obviously it's closer to us comparatively as compared to the other stars that we see in the night sky. That is the reason why it appears bigger, and moreover it has a continuous flow of light in the daytime. That's why it doesn't twinkle. So this is the very first point. I hope you must have understood. Second thing, let's move on to our second particular point up here, which says about the sun rising a few minutes earlier and setting few minutes late from the horizon. So this thing is, let's assume the horizon edge. Now horizon, what exactly it is? If you're on a beach, this side is the sea and the above one is the sky, and the line, the imaginary line where we see that the sea or the ocean actually meets the sky is called the horizon. So you can see the kind of landscape which small kids make when they are drawing something or they're painting. So the sun rises somewhere from here. But when the sun rises up, even in terms of, like, let's say if it's early morning, before the sun rises up, or you can say when it's just below the horizon line, the sun appears to be a little above. Why? Because of refraction of light. In the same way, like I discussed, that if we drop a coin inside a pool, it appears to be a little, higher. The actual depth is not really visible. It's the apparent depth that is visible. The same way up, when the sun is coming up, it will be visible before it actually comes up above the horizon. And the same phenomena happens when it sets down. Even when it is under the horizon or below the horizon, still we will be able to see the sun for a few minutes of time span just because of refraction of light, the phenomena that is apparent depth and real depth. Then this was the second point. I hope you all have understood. The third one, let's move on to. The third one says water tank appears to be shallow. Shallow means less deep, opposite of deep, you can say. Then it's real depth. So the actual depth of the tank, if you're looking at a tank filled with water and you're trying to assume its depth, you will not be able to actually see or assume or observe the real depth. You will just be able to assume or see or observe the apparent depth because of the same phenomena of refraction of light. And this is exactly what happens through that. This is exactly what happens, that when we look at a tank, then it appears to be shallow, less deep as compared to its actual depth. So shallow is the depth being less because of the refraction of light happening there. The fourth one is already discussed up, so that's all are some of the applications of the refraction of light. There are though more other than these, which can be studied further in the book with the reference of some books. These are some of the basic ones which we must know, all of us. Now, coming up to the next topic. Now, the end of our part B. This was the end of our part B of optics, and we're gonna soon be coming up with our part C of optics, which is critical angle and the total internal reflection. Until then, please stay tuned. Kindly, you can subscribe to this channel, which is Backbenchers Academy by Rohit Verma, so that whenever I upload any video, you get the notification. And I would definitely appreciate if you can put up any feedback or a comment regarding the videos, and give me suggestions regarding what else can be added on, or what innovations can I do to the video so as to make it more interactive, make it more user friendly, so that you actually get more of knowledge out of it. So that's all for the day and for this video, and stay tuned. Thank you so much. This is Rohit Verma signing off. Thank you.